Good morning, everyone. We are going to mostly be in chapter 10 today. We're going to do a demo out of chapter 9, though, here in a moment. But just to get us started here in chapter 10 this morning, the idea of chapter 10 is we're starting a unit on gases, liquid, solids, with chapter 10 being on gases. So we'll talk about properties of gases. We'll talk about pressure. We'll get into the gas laws, the ideal gas law. You might remember this law. I like to start with something that we may already know if you've seen this before. PV is equal to nRT is the ideal gas law. PIV nert is sometimes what we call this equation. It relates the pressure of a gas, the volume of a gas, to the moles of a gas, to the temperature, and then the gas constant, R. And we'll get into where this equation comes from and what it is, but you may have seen this equation before, but we'll be talking about the ideal gas law in this chapter. We'll talk about some applications of the gas law. We'll get into gas mixtures, partial pressures for having more than one gas present. Air is a very good example of a gas mixture where air is a sample of about 78% nitrogen and 21% oxygen. So we'll get into mixtures of gas such as air, which we know is a good example of a mixture of about 78% N2, 21% O2. Does anybody know the next most abundant substance in air? It's actually argon. So argon's about 1% of air. Switch this around here. So about 1% is argon. And then less than a fraction of the remaining components are things like CO2, water vapor, other substances. These are a smaller component. So these are much less than 1%. And so a lot of other components of the atmosphere, a lot of the things that are really important in the atmosphere are a very small component of the atmosphere. An interesting sidetrack for the moment would be that if you think about these substances here, the major contributors of what we think of as being air, they're not capable of absorbing infrared radiation in the way that greenhouse gases can absorb infrared radiation. So you're going to see more heat trapping. So the substances that are a very small component of the atmosphere are really the only components that are capable of holding on to heat that's radiating from the surface of Earth and play a key role in the sort of temperature characteristics of Earth. So one of the reasons why CO2 is such a small component of the atmosphere, yet a very important molecule in the atmosphere, is due to that greenhouse capabilities. And then the major components here, these are not greenhouse gases. So that's interesting to talk about. That relates back to something we'll talk about in this chapter relating gas mixtures. We'll talk about the behavior of gases through the kinetic molecular theory of gases. This just helps us understand how gases behave so we can kind of come up with a model for describing how gases behave in a typical container. Then we'll talk about effusion and diffusion. Effusion is the escape from a pinhole. Diffusion is the rate that a gas travels through a medium. So think about somebody's cooking downstairs. Diffusion is how long the scent of the cooking takes it to make its way upstairs. And so you can think if somebody brews a cup of coffee within a minute or two, a couple rooms over, you usually smell it. That's diffusion. If you think of a hole in a tire where you're losing air out of a tire, that's effusion. So escape from a pinhole and then moving through a medium. And then finally, we'll get into real gases where we have a breakdown in the ideal gas law. And one of the interesting things with with quote unquote real gases is we start to get towards the description of liquids. So when gases start to get sticky, when gases start to get close to the condensation point where molecules begin to start to condense. So think about having water above the boiling point of water. So imagine you have a water vapor sample. It could be water off a stove. So you're boiling a pot of water. And so the steam coming off your water is at 100 degrees or greater. And then you can think of how when that temperature cools back down, obviously the water is going to condense back into water droplets. This is why you see, above your stove in the hood, you see water condensing. Or on the window nearby, you might see water condensing as well. And so we know that eventually a gas, if you cool it, will turn into a liquid. When you get close to that boiling point where the substance still is a gas, the molecules start to be sticky together and they start to have and experience their intermolecular forces of attraction. So we'll try to describe that. And then that'll send us, of course, into the liquids chapter after chapter 10. I think this is probably a good moment here to head back, just to kind of try to do this experiment here to see if we can really sort of see something like what this picture is showing us here. So let me switch over to the document camera. And so So we have a magnet here. And so the idea will be, first, can I cool it down because I'm supposed to make the magnet cold first, but then also I'm going to pour liquid nitrogen over it. And so liquid nitrogen is not supposed to be paramagnetic. So if I flow nitrogen over this magnet, the gaseous nitrogen shouldn't stick. And so let's see if we can see this. And so this container here, this dewar has liquid nitrogen in it. And so I'm just going to pour some liquid nitrogen over the magnet. I don't think this is too dangerous for you folks up front, but if you're worried, you can step back. Are you guys worried? And so the question is, do you see nitrogen sticking? I can't really look, but do you see the liquid molecules like sticking in between the magnet? And this might be a little bit easier if I turn the lights down too to see. So again, the question is, do you see the nitrogen sticking between the magnet? I have a hard time seeing it, but do you guys see nitrogen sticking between the magnet? You shouldn't, so hopefully that was the case. And so then the way we get liquid oxygen is you're not just going to buy liquid oxygen, because liquid oxygen would be pretty explosive. So you see, have you ever seen those big Praxair white trucks that have like the green whiting Praxair, a big white, it looks like a gas tanker truck, but it looks neater and cleaner. If you've ever seen those, that's actually liquid nitrogen. So you can actually have liquid nitrogen filled. If you've ever looked behind Celeste's lab, in between Evan's lab, there's that big, huge white tank that's filled with liquid nitrogen. That's where we go fill our container so we can get liquid nitrogen. But the way we get liquid oxygen is we just take a test tube and submerge it in the nitrogen. Like you see here, I have a test tube in liquid nitrogen, so that inside the test tube, it's just going to be condensing air, because the boiling point of oxygen is just above nitrogen. So if we have a test tube of liquid nitrogen, that's cold enough to trap out liquid oxygen. It's also cold enough to trap liquid nitrogen. So in my test tube here, what I should have is basically just a condensation of nitrogen and oxygen out of air. It's actually not cold enough to condense the argon. Not that that matters too much, but we're not going to see, or we wouldn't expect to find argon in this test tube. But so I have a test tube here that's filled with liquid nitrogen and oxygen. And so now the oxygen here hopefully will stick in between the magnet. You guys see the nitrogen, so for a moment or two, you can see the gas sticking in between the magnet. Let's see it again. So you see, just for a moment, you see how the vapors are kind of sticking in between the magnet. So that's showing us and giving us like kind of some solid evidence with our own eyes, with our own experiment, that oxygen's behaving as a paramagnetic molecule, unlike nitrogen, which is diamagnetic. And so we can do one quick last test and just go back to the nitrogen for a minute and make sure that we see that the nitrogen isn't doing this again. So once we saw oxygen doing it, and we can see nitrogen not doing it again. So that's the difference between the behavior of oxygen acting as a substance that has unpaired electrons versus nitrogen, the substance that doesn't have unpaired electrons. And so oxygen's paramagnetic, has unpaired electrons. We saw that from the MO diagram, helped us see where it has two unpaired electrons, if you recall, in that pi star orbital. And then nitrogen just doesn't have those same unpaired electrons. So no unpaired electrons for nitrogen. Okay, so I just thought, whoops, just hit the wrong source button. So I just thought it was useful to kind of see an example of that picture here. So you can see the picture, we're just more or less seeing the picture in front of us, but just trying to replicate that we're not making up that oxygen has unpaired electrons, of course. Okay, so with that, we'll head back into chapter 10. We'll really get our start in chapter 10. And so, take this coat off too. So some properties of gases is that gases behave similar to other gases. So the physical properties of gases are all pretty similar. We remember the key characteristics of gases is they expand to fill their containers. They're mainly comprised of non-metallic elements. Like you don't see things like sodium or other metals existing as gases at room temperature. It's predominantly the non-metallic elements, things like hydrogen, oxygen, nitrogen, etc. Chlorine and fluorine Cl2 and F2 are also substances or elements that exist as gases at room temperature. Molecules can be gases at room temperature, like CO2 is a gas at room temperature. And so, of course, gases expand to fill containers. You can compress a gas. If you had a cylinder, you can have like a piston where you can compress the gas. You probably can even imagine if we're going to press down on a piston onto a cylinder of a gas, we're going to be increasing the pressure. You probably already have an idea that if you cut the volume and decrease the volume of a gas, and you're going to increase the pressure. Gases tend to have low densities because they're expanded in their containers. So gases are expanding in their containers, so their densities are low compared to gases and liquids, or compared to liquids and solids. And then if we have multiple gases in a container, as long as they don't react together, as long as there's no reaction taking place, then they're both just going to coexist in the container. So a gas is an idea, or the main idea that we'll see with the kinetic molecular theory of gases is a particle just bounces around its container. It might bounce off another molecule, but they're not really sticking together. So we're assuming when we have a gas that the particles aren't forming intermolecular forces and sticking together, that if they collide, they just bounce off each other. And then we can have multiple substances. If we have O2 and N2, like in air, those molecules bounce into each other, they just deflect off each other, they don't react together. So we can have mixtures, but they're always going to be homogeneous, meaning mixed perfectly. So if you have a gas mixture, you're not going to have the heavier molecules at the bottom, the lighter at the top. A gas mixture, because the particles are always in motion, just will always be randomly distributed in the container. So our gas mixtures are always on the homogeneous side, so equally mixed in the container. So now some other characteristics that we can define or sort of are related to each other are the temperature, pressure, volume, and the amount of gas that we saw with that ideal gas equation. I like to lead with this equation just because you've probably seen it before. But if you haven't, we'll kind of show a quick derivation of it a few slides from now. So the temperature of a gas is, of course, T, pressure is P in terms of our equation, volume's V, the amount of gas is moles, is N. And so N is equal to moles, and that unit volume, we're going to see like a lot of common units used here. We're going to use our liter unit most often for the volume. We need to talk a little bit about pressure, but you're going to see a unit called the ATM. If you haven't seen this before, or atmospheres is going to be one of our key units that we use here for pressure. And then temperature. In this chapter, almost every example, in fact, I think every example in this chapter has to be in Kelvin, and we'll talk about why that's the case in a few moments as well. So, or at least we have to get to some absolute temperature scale where the lowest temperature can be is 0 Kelvin. So we need a temperature scale where temperature can't go negative. So we're going to need to use something like Kelvin here for temperature. And so let's start with what pressure is and kind of get an understanding of pressure. So pressure from like a physics standpoint is defined as a force applied to an area. And you can think of force as a mass times an acceleration. So if you're thinking force is a mass times acceleration applied onto a surface area, that's the idea of pressure. So if you're forcing, if you're pressing down on that piston, what you're doing is you're applying a force that's increasing the sort of applied mass onto the square area. So by pressing down on that gas cylinder to increase its pressure, what you're doing is you're causing more collisions to take place. You're applying more mass to hit that square area inside the container. So that would be increasing the pressure through that process. Now, what atmospheric pressure is due to, if you think of on the surface of Earth, we have a pressure due to the atmosphere, and that's due to the gravity that's accelerating the atmosphere towards the surface of the Earth. And so atmospheric pressure is the weight of the atmosphere that's being accelerated by gravity onto the surface area of Earth. And I thought it was just kind of interesting that you can actually kind of look up the sort of mass of the Earth, and it's about 6 times 10 to the 24 kilograms. I wanted to look at the mass of the Earth just to get a sense of how light the atmosphere is in comparison. And so the mass of the atmosphere is about 1/millionth the mass of Earth. So it's about 5 times 10 to the 18 kilograms. And so that's the sort of approximated mass of all the substances in our atmosphere. The surface area of Earth is calculated to be about 5.0 times 10 to the 14 square meters. If you were to look this up, you usually see the unit in like square kilometers or square miles, but I just gone ahead and converted that for us here into square meters. And then gravity on Earth's about 9.8 meters per second squared. And so we can calculate the atmospheric pressure that's being caused by the mass of the atmosphere. So the mass of the atmosphere being 5.15 times 10 to the 14 kilograms. So that's the mass of our atmosphere. The force of acceleration is gravity acting on the atmosphere, so that's 9.8 meters per second squared. And then we're dividing that by the surface area of Earth, which is 5.0 times 10 to the, oops, I mixed up my 14 and 18. So the mass of the atmosphere is 10 to the 18. And then the surface area is 5.0 times 10 to the 14 square meters. And so if I work out that math here, so 5.15 e to the 18 times 9.8, and then I divide that by 5.0 e to the 14, I get about 100,000. It's 100,940. So we'll round that to 100,000. So we'll say that's from sig figs here, about 100,000. And the units would be kilograms, meter to the minus 1, because I have meters here and divide by meters squared. So that results in meters to the minus 1, and then seconds to the minus 2. Or kilograms per meter per second squared is another way you can write this unit. Now, the unit kilogram, meter to the minus 1, second to the minus 2, those are, the fundamental SI unit of mass, if you recall from chapter 1's kilogram. The fundamental SI unit for distance is the meter. The fundamental distance for time, or the fundamental unit for time is seconds, of course. So these are our fundamental or our base SI units. And the reason why I point that out is it's always the kilogram, not the gram. That's the base SI unit. Well, that's used to determine or relate to the SI unit of pressure, which is the Pascal. So Pascal is the SI unit of pressure. And so the SI unit of pressure, 1 Pascal, is defined to be precisely 1 kilogram meter to the minus 1, second to the minus 2. So in other words, our atmospheric pressure is equal, from our calculation here, to be about 100,000 Pascal. And Pascal's oddly not used that often, even though it's the SI unit of pressure. So this is our SI unit of pressure. It's not all that commonly used. We'll see the ATM's more commonly used. And the nice thing with the ATM, you'll see the standard atmospheric pressure is just 1 in that unit. But in this fundamental SI unit, kilograms, meter to the minus 1, second to the minus 2, the force that's being caused, the force due to gravity of the atmospheric mass onto the surface area of Earth gives the pressure to be about 100,000 Pascal. And so then if you think of a 1 meter by 1 meter column, so if you think about this much above that sort of distance into the atmosphere, so if you imagine going out into the oval or whatever, kind of carving out that meter and kind of like looking straight up into the atmosphere, that's about 10,000 kilograms of atmosphere above that square meter, because you got about 10,000 kilograms being forced at about 10 meters per second squared to give you that unit of about 100,000 kilograms, meter to the minus 1, second to the minus 2. So that column of error has a mass of about 10,000 kilograms, 10 to the 4 kilograms. So that's kind of interesting to kind of think about. Just, we don't really think about how much mass is above us. The weight of the atmosphere is actually quite extensive. But anyways, that's what atmospheric pressure is due to. It's due to the weight of the atmosphere, gravity, and then the surface area of Earth. And so 101325 precisely is what's defined to be standard atmospheric pressure. So standard atmospheric pressure, this is on the next slide for some conversion, or actually, yes, it is on this slide. For some conversion factors, this is what we think of as being in Pascal standard atmospheric pressure. And so 1 ATM is standard pressure in the unit of ATM. So you can think 1 ATM is about the average pressure on Earth. So we call that the atmosphere unit. So 1 ATM is precisely 101325 Pascal. And this is like exact with these 6 digits here. So this isn't rounded. So it's precisely this 101325 exact Pascal and 1 ATM. You can relate that to bar. The unit bar is not commonly used in this class. It's more used by meteorologists. Any chance we have a meteorology major in the class? Anybody? Every now and then we get somebody studying meteorology. Obviously, they're going to use the bar, the millibar units more commonly for relating pressures for weather events. And so you can see though that the conversion to bar, it looks very much like Pascal just divided by 10 to the 5. And then we can also relate that to a value we use more commonly in day-to-day usage of PSI, like if we're filling a car tire, we're usually using the unit of pounds per square inch. And so that's PSI. And so that's the pounds of force per square inch. And so that's the PSI unit. We don't use that unit a whole lot in this class either, but I think it's useful to talk about a few units that are used in everyday life. One thing that's kind of interesting, if you're filling your car tire, which if you guys drive, anybody drive? Not a lot of freshmen have cars, but I'm sure you had cars in high school. But you know, on a cold day, sometimes your indicator says, oh, your tires are low on pressure, and you have to go find like somewhere to fill your tires. And so, of course, when the temperature goes low, the pressure is dropping in your tire. We'll talk about why that is according to the ideal gas law in a few moments. But when the pressure drops, of course, you have to put more air in the tire. But when you read the gauge pressure, usually you're filling your tire, say, to 35 PSI. When you fill your tire to 35 PSI, that's above atmospheric pressure. So the gauge reading you're getting is the pressure inside the tire above standard atmospheric pressure that day. So in other words, if you have a tire that's completely flat, and you put a gauge reader on it, it doesn't read at all. If you imagine the little thing you put on where the arm extends and tell you the pressure in the tire, and it doesn't move at all, that's telling you that the tire is at atmospheric pressure, that it's at zero pressure beyond atmospheric pressure. So this is usually a gauge reading. This is more for your understanding of pressure. It also kind of relates back to, you guys, some of you have probably heard about the Deflategate scandal of Tom Brady. This is, again, probably not something you guys might remember. Some of you might remember this when you were kids. But there was this scandal, did the New England Patriots deflate footballs? And there was a lot of discussion of the ideal gas law and what the pressure should have been in a football when it went from a warm room to the cold stadium. But what everybody was confusing is that when you fill a football to 8 PSI, that it's really 8 plus 14.7 PSI, because standard atmospheric pressure is 14.7 PSI. So everybody was screwing up the basic math that they were doing to try to calculate what the pressure should have been in the football. And if you actually do the right math, I don't think the footballs were being deflated intentionally or anything. But anyways, not that I care. But you may have heard about that scandal. Kind of relates back to the unit of PSI. Now, 1 ATM into another unit that we do use more commonly is torr in millimeters of mercury. And so the ATM unit into torr or millimeters of mercury, it's weird that we have two different units that have the same conversion factor. So there's 760 torr or 760 millimeters of mercury. This should be a G, figure, cut it off. That's millimeters of mercury. Relate to the ATM unit. We will use those conversion factors more commonly. So these are probably the conversion factors we actually use the most in this class. But now the reason why you see the millimeters of mercury as a unit for pressure is that has to do with how a barometer is constructed. So a barometer is a very interesting device because what you do to make a barometer is you take a glass tube. If you can imagine, we put a vacuum on the glass tube. We evacuate all the air out of the tube, and then you take the tube and you submerge it in a dish of mercury. And because the tube's evacuated, you can imagine mercury is going to be pulled up into the tube. But how much mercury? Well, the amount of mercury that's going to be pulled up or sucked up into the tube is related to the mass that's being pressed down upon the dish by the atmosphere. So the dish has atmospheric pressure acting upon it, and that's pressing down on the disc. And then if you think inside the container, there's no vacuum, so the mass of mercury inside this column here is going to equal the amount of atmospheric force or weight that's sitting above that sort of cross-sectional area. The basic idea is mercury has a really high density. The density of mercury is 13.5 grams per milliliter. Density, 13.5 grams per milliliter. And so you can think, if we're counterbalancing the mass of the atmosphere with the amount of mercury inside this column, that if we chose a liquid that had a lower density, like water's density is of course 1 gram per milliliter, then we need a column that was 13.5 times higher in order to measure the atmospheric pressure. So if we used water in our dish instead of mercury, we'd have a very tall column that we'd have to make. It would be 13.5 times taller. And so if you think of 760 millimeters, that's getting close to a kilometer. So you need a barometer to be about 1 to 2 kilometers to be able to measure standard atmospheric pressure. So even a mercury barometer is going to be about yay big in terms of its size, but you can imagine it's going to be 13.5 times bigger if we use water. If we use a substance that was even half the density of mercury, it would then be double the size in terms of the height that we would need to be able to measure that height. Again, we don't use barometers too much anymore. You can use a gauge reading to measure atmospheric pressure, but if you want an accurate reading of the atmospheric pressure, you could use a barometer and you're just reading the height differential off the column, and that's telling you in millimeters of mercury what the pressure reading is that day. Now, I like to mention what a barometer is just so you can have some understanding. That's where mercury comes into play. So it just comes into play that that's what we use to make up our barometer. You could, in theory, have other millimeters of other substances, but really mercury is the common unit here and the common substance that's used in most barometers. Okay, we can do a couple pressure conversions. I think this is really where just understanding that there are some different pressure units, and then we, of course, give you the conversion factors. We don't expect that you memorize any of those conversion factors on the previous slide. So if we want to convert 745 torr to millimeters of mercury, that's the weird one where this is exact. So this would be just 745.0 millimeters of mercury, because 1 torr is equal to 1 millimeter of mercury. And I'm picking that up from the conversion factor that there was 760 torr. Exactly, the reason I'm putting the period sign in the previous page is that there's exactly 760 torr. It's not a rounded number, but 760 exact torr and 760 millimeters of mercury. Hence, it's 1 to 1. If I want to calculate the number of ATM, so the atmospheres of the gas, I would calculate this by taking the value 745.0 torr or millimeters of mercury, and then just using the conversion factor, there's 760 torr precisely in 1 ATM. Now to go back to sig figs real quick, do you think I should round this to 2 sig figs or keep 4? What do you guys think? I'm going to keep 3 because this is an exact conversion. So there's exactly 760. So I don't need to round to 2 sig figs here because I'm not rounding, I'm not measuring, there's about 760. It's not like there's between 750 and 770 torr in an ATM. That's not what we mean here. There's exactly 760 torr in an ATM, so we can use that exact conversion factor. If I want to convert to Pascal, even though, like I said, we're probably not going to really do this conversion. I doubt that there's going to be a need to convert to Pascal, but if we did calculation, we can do it a few ways. Let's start with the 750 torr or 745.0 torr. We can use the conversion factor that for 1 ATM, 760 torr is 1 ATM, and then 1 ATM is 101.325 Pascal. I could have just said, well, 760 torr is 101.325 Pascal as well. I probably could have done this in one step if I thought about it as well. But I'm just using the common unit of the ATM to help me make this conversion. I could have, of course, just also ran with the 0.9803 ATM above and just continued from that step as well. But I just want to make sure we see how do you convert from torr into Pascal, from ATM to Pascal. We're just using that common unit of the ATM. So this is 99,330 once I round to 4 sig figs. It's a lot of Pascal, so just under 100,000 Pascal. And then if I want to go to PSI, the conversion factor for PSI is that for every 760 torr, that's 1 ATM, that's 14.696 PSI. And again, you can use the values, like you'd have the conversion factors provided. You wouldn't have to have them memorized. So that's 14.41 pounds per square inch. Okay, so just a few conversion factors. And again, I think the key ones are going to be millimeters of mercury. We'll also say torr. We'll use those a lot in units, and also the ATM unit. So those are going to be the primary ones that we see the most in chapter 10. Now, let's talk about how you measure the pressure of gases. This slide here is kind of in a weird way dated just because, if you want to measure a gas pressure these days, you would just use a pressure gauge. I mean, we can show you how they used to do this before pressure gauges became common or in some cases invented. What was used originally was something called a manometer, which is like a barometer. And so what a manometer looks like, just to give you an idea of how this used to be done. So imagine you have a gas sample. What you would do is you'd have it in like a gas container. You'd have a valve here that you could have closed. And then before you open the valve, you would start with your manometer with equal levels of mercury. So you'd begin with a closed valve, equal levels of mercury, and then you just simply open the valve. And so you open the valve, and if the gas is higher than atmospheric pressure, then you get a differential that looks like on this graph here. And so here, the pressure of the gas is greater than atmospheric pressure because the pressure is pushing the mercury down in the sample side and then pushing it up in the sample connected to the atmosphere. So you have the atmospheric pressure pressing down on the one end, you have the pressure of the gas pressing down the other end, and the height of the mercury just counterbalances the two. And so then you could also imagine a case where the gas was under a vacuum. So you could have a container of a gas that was less than atmospheric pressure, and that would look something like this. So if you open up your column, so you start with your gas container, you connect it to your manometer, like so, and you have your mercury columns relatively equal when you start. So then you open your valve, and then if this column goes upward and this one goes downward, and you get the opposite side, then that's the mercury being pulled upward because of the less pressure being applied to counterbalance the mass of the atmosphere. And so what you're looking for is the height differential. I don't think you ever really use this equation too much, but you would measure the height column difference in something like millimeters of mercury. You would relate the two to the atmospheric pressure in the same unit. So what you'd want to have is the pressure of the atmosphere in something like millimeters of mercury, and you'd want to plus or minus the pressure of your height here also in units of millimeters of mercury. So you literally measure the height differential of mercury. But again, not really something commonly done or a problem I think that will ever come up. But this is how we used to measure gas pressures, is using something like a manometer. And I just want us to think how mercury kind of is commonly used, again, because if you want to make a manometer out of a different liquid, you're just going to need a much bigger manometer than if you just use mercury. Okay, so let's get into the gas laws that relate changes in pressure versus volume versus temperature in terms of how they relate together. And we were already thinking of the relationship between volume and pressure when we were thinking about pressing down on that piston and cutting the volume in half. And so Boyle, I suppose, was the first to study the relationship or think about putting like a graph to this in terms of what's the pressure versus volume relationship. And so if you take your volume on your y-axis and you're changing the volume, so here we're going to cut the volume in half and decrease the volume. And then what we're going to do is increase the pressure as a result. So if we go from a volume of our container of 1 liter, we cut it down to half a liter, that pressure is going to increase as a result. And so we have an increase in pressure. So pressure is increasing as we're decreasing the volume of our container. There's an inverse relationship between those two values, exactly like we predicted before. So again, volume, if you're going to decrease the volume, then the pressure decreases. So that's an inverse relationship. So we get an increase in pressure when we decrease the volume. So you get this like inverse relationship between volume and pressure. But then you can imagine, well, what if we took a different type of container? Maybe we also can picture a piston inside of a gas mixture where the gas, like it's an airtight container, but that piston is just going to maintain a constant pressure. So if we do something to increase, or that might try to increase the pressure of the container, the volume is just going to expand, the piston's going to go upward. And so we can maybe imagine we have sort of a movable piston here that can go up or down. Maybe we're going to put this entire thing into a water bath where we can change the temperature of the water bath. And so inside the container here, we have our gas particles. And so we can imagine that piston just maintaining a pressure And so what happens if you increase the temperature of the water bath? So we send the water temperature bath upward, and so the gas inside the container is going to increase in temperature as well, because it's going to sort of rise with temperature as the water bath temperature changes. And so if we increase the temperature of the water bath, then the volume is going to expand as we increase the temperature. We're going to give those particles more energy. They're going to be moving faster. They're going to hit the particle walls more often. They're going to expand the volume of the container. They're going to do work on the surroundings. That's just to kind of relate this back to chapter 5 a little bit. But the molecules are going to work on the surroundings, and so they're going to move the surroundings out of the way. If we're thinking of the W for this process here of increasing the temperature, W would be less than 0, just to kind of give us, this has nothing to do with chapter 10 per se, but it just gives us another way of thinking expansion is the system doing work on the surroundings. But then if we decrease the temperature, if we instead said, well, take the temperature downward, so imagine you're at a temperature here, we decrease the temperature, we're going to then decrease the volume. So if we put ice into our water bath, we're going to see the piston move downward because the molecules are going to slow down their motions, and then that's going to pull the cylinder downward. And so with increasing temperature, we have work being less than 0, decreasing temperature, work being done on the system. The volume will decrease as a result of that temperature change. And so this is a direct relationship. So if you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume. So you have a, from Charles' law, presumably being the first to study this or put a graph to this, finds that there's a direct relationship between volume and temperature. Increase the temperature, you increase the volume of the gas. Before I move on to that problem, let me put a couple of thoughts here into Boyle's and Charles' law. One of them is that if I had a pressure volume, and when I'm thinking of changing the pressure and volume here, I'm keeping a constant amount of gas and I'm keeping a constant temperature. And so that the pressure and the volume are going to be equal to a set of constants here. And then I can imagine if I change the pressure and the volume and nothing else, I don't change, like it's an airtight container, the temperature is constant, I'm not changing any of the other variables. And so this would be a constant, temperature, constant amount of gas. So we're not changing those two variables. So as long as I keep those two variables in check and keep them constant, then I should be able to start with a pressure volume set of conditions I call P1 and V1, and then I can change them into P2, V2, into a new set of pressure and volume conditions, and they must be equal together because they're going to be equal to the same set of constants. So pressure times volume is equal to some set of constants, and I take my initial pressure, my initial volume, I can then change them because they both have to be equal to the same set of constants, so therefore they're equal to each other. And so that just means that we can sort of change our pressure. This is just the idea, if you double the pressure, then you should cut the volume in half. As a result, is going to, in the next problem, we'll kind of mathematically work through that. And then the volume temperature relationship is that volume over temperature is equal to a set of constants, and it has a constant now pressure and amount of gas because we're not changing the pressure. So we're assuming that that piston was keeping a constant pressure, and it was also airtight, so we're not losing any of our gas. And so we'd have V1 over T1, our initial set of conditions equal to some set of constants. And then we'd also have V2 over T2 equal to the same set of constants, so therefore they have to be equal to each other. So we can write V1 over T1 is equal to V2 over T2 from the Charles law. So we're just kind of realizing that volume over temperature equal to constants, but it's pressure times volume equal to constants. If you also come back to, I always like to kind of say, sometimes we look at problems where we haven't yet defined precisely in the textbook the key equation we're going to use. But if you jump ahead and kind of use the equation here, you can kind of see the math kind of falling out here, that pressure times volume is equal to these constants here, and then volume over temperature would be equal to NR over P. So you can kind of see that the equations falling out of the ideal gas law. You can see PV is equal to these constants, so P1, V1 equal P2, V2, because they're both equal to the same nRT as each other. And then V over T is equal to NR over P. So if you change V1 and T1 and you maintain them into V2 over T2, they have to, by ratio, still be equal to N times R divided by P, so they have to be equal to each other. Okay, so a couple of problems. Let me actually So again, I just wanted to make sure to set up some of the math behind these two problems that I think are relatively straightforward. I hope we can look at these two examples and make sense of them. So we have 2 liters of a gas sample at a pressure of 2 atmospheres. And so we have 2 liters of gas at 2 atm. At what pressure would the sample, or what pressure would the sample have if the volume of the gas is reduced to 1 liter? So we're going to cut the volume in half, and we're going to do this at constant temperature without any loss of gas sample. So these two statements here, at constant temperature without any loss of sample, those are just telling us that we have constant N and constant T. So the only 2 variables are pressure and volume. And so if our only 2 variables are pressure and volume, we have PV, P1 V1 equal P2 V2. And then we can solve for the P2. So P2 is what we're looking for. P2 will be equal to P1 V1 divided by V2. We're cutting the volume in half, so we're expecting the pressure to go up. So we take our P1, 2 atm, times 2 liters, and we divide by 1 liter for V2. And so, of course, that gives us a pressure of 4 atm. So cut the volume in half, we can calculate precisely with our equation that you double the pressure. Now, the next question becomes maybe a little trickier in a way, because we have to come back to like thinking of absolute temperatures before maybe we realize we have to think about absolute temperatures. But you guys can more easily, if I flip back now, it really screws up the video. But if you look back at the previous slide, notice that temperature, we want to start with the temperature that doesn't flip negative. Like if you look at the graph that was looking at V versus T, if temperature changed to a negative number, our graph would look kind of funky. So we need to have a temperature that's always positive. We don't want temperature to change sign, because we don't want to like flip and say, like if temperature goes below 0 degrees Celsius, we wouldn't want the conclusion to be that the volume somehow flips to be -2. That wouldn't make very much sense. So we have to use a temperature scale like Kelvin, where the lowest attainable temperature is 0 Kelvin. So we have to use an absolute temperature scale. So we have a gas cylinder with a movable piston, which maintains a constant pressure. So pressure is constant. And so we have a volume of 2 liters at 25 degrees C. And so what's the volume of the gas at 50 degrees C? Now, the very convenient answer would be 4 liters, right? So the answer, you may be thinking, well, I'm doubling the temperature, so the answer has to be 4 liters. But not so fast. We have to think, well, what is this temperature on an absolute scale? So 25 degrees C plus 273 Kelvin, that's 298 Kelvin. And so then when we look at 50 degrees C, that's 50 plus 273 Kelvin, that's going to be 323, just silly math, of course it's 323 Kelvin. And so our temperature is actually not increasing by a factor of 2. Our temperature is only increasing by a smaller factor. It's only increasing by 323 divided by 298 Kelvin. So we just have to think here, when I have my V1 over T1 over T2, and I'm trying to calculate my V2 here, the volume at the new temperature. So I'm trying to solve for V2 by having that equal V1 T2 divided by T1, that these temperatures have to go into the Kelvin scale. So we just have to go into an absolute temperature scale. Now, here's another question. Does anybody know the absolute temperature scale but based on Fahrenheit? Has anybody ever heard of this scale? It's called Rakin. Theoretically, you could use the Rakin scale here too. So you don't necessarily have to use Kelvin, you just have to use an absolute temperature scale, but the only common one that we use in science class is Kelvin. But you can look at there's a temperature scale where you can make Fahrenheit to be at most 0 Fahrenheit, and it would be like minus 496 point something degrees Fahrenheit to convert into that scale. So theoretically, you could use that scale too. But more commonly, we're going to use Kelvin here. We just have to use an absolute temperature scale where the lowest temperature is 0 Kelvin. We don't use degrees, but 0 Kelvin is the lowest possible temperature of any substance in the Kelvin scale. So that's why we're converting into Kelvin here. So we go 2 liter gas sample times our new temperature, 323 Kelvin. Of course, we're increasing the temperature. We're expecting the volume to expand. it's good if we have an idea of what the volume is supposed to be, because it's really easy to flip our temperatures here. But we're going to get expansion because we're increasing the temperature. Oh, I put the wrong, it should be 298 too. I put the conversion factor here. I need to put 298, the initial temperature, not 273. So again, it'd be 2 times 323 divide by 298. That gives me 2.17 liters. So the volume goes up a little, but it doesn't double. In order to double the volume of the container by increasing the temperature, we'd have to double 298 Kelvin. We'd have to go to like 500 Kelvin. We'd have to go to like 300 or so degrees C. So we'd have to really, really increase the temperature of this container to double the volume. So we're going to increase the volume to 2.17 liters by going from 298 to 323 Kelvin. So again, just have in the back of your mind in this chapter that almost nothing will be in degrees C in chapter 10. So everything is almost going to have to be in this Kelvin or absolute temperature scale within this chapter. Now the last of our gas laws is Avogadro's law. So Avogadro was one who was counting particles, and so that's the relationship between volume and quantity of gas. And this one's pretty obvious, that if you put more air into your tire, it's going to expand to a greater volume. And so this is at constant pressure. So maybe like filling a tire is not the best example, but this is constant pressure and temperature. So if you imagine you have a balloon and you're going to put more and more air into a balloon, it expands, and generally the balloon is acting to expand so the pressure inside doesn't go up by much. It's kind of maintaining a constant-ish pressure. And so as you put more gas into a container, you're expanding to a greater volume. And the other observation of Avogadro is an interesting one, is that if you took 1 mole of any gas, that they have the same volume. So if you take a mole, so if you take 4 grams of helium, that's 1 mole, because the molar mass of helium is about 4.00 grams per mole, N2 is 14.0 times 2, so 28.0. This is 1 mole of N2. If you take 1 mole of CH4, that they all have approximately the same volume, and even more precise is 22.415 liters is the volume of 1 mole of a gas at what we call STP. So STP is standard temperature and pressure. So standard pressure is 1 atm, so that's easy. We were talking about that earlier. That's our standard atmospheric pressure. But then the standard temperature is actually 0 degrees C. So these two markers here are what we call STP. So standard temperature and pressure. And again, it's 1 atm, but 0 degrees C. Or precisely 273.15 Kelvin. Not a big detail. To be honest, there's, did any of you guys take AP chemistry? Where's my AP crowd? A few of you guys. Did any of you guys take, does anybody ever take like a chemistry Olympiad exam as like a contest in high school to see who scored the highest? See a few people shaking their heads. They love STP is 0 degrees C. And they have like, every test will have like 2 questions where if you think it's 298 Kelvin, you get the answer wrong. And I don't know why they care so much, but it's not 298 Kelvin, it's 273 Kelvin. So if we say STP, the key is that it's 0 degrees C. And it's always like a trick question on a lot of tests. I don't know if like I said, I do have a couple of questions on my daily quizzes that kind of reinforce that it's 0 degrees C, not 298 Kelvin. But for whatever reason, you see a lot of tests, like AP tests, like to test this, and like chemistry Olympiad exams, like to really nail down that this is 0 degrees C, not 298 Kelvin. But to me, the bigger thing is that if you're at that temperature, that pressure, that's your constant temperature and pressure, that 1 mole of the gas has the same volume. And so what makes a gas have a particular volume is the number of particles. So when you have a mole of helium, you have 6.02 times 10 to the 23 helium atoms as your particle. If you have a mole of nitrogen, you have 6.02 times 10 to the 23 N2 molecules. So you have that number of molecules. If you have CH4, then you have that number of molecules of CH4. And so the number of particles, when you have a mole of CH4, you just have a mole of 5 atoms stuck together that are flying around the container together. If you have a mole of N2, you have 2 nitrogen atoms flying around the container together, stuck together. If you have a mole of helium, you have 1 single atom flying around the container. So it doesn't matter how many atoms are stuck together. The only thing that matters is how many total particles are there. Not the total number of atoms, it's the total number of particles or the total number of moles inside the container that matters. Now, one of the interesting things from putting this all together is that we then lead to the ideal gas equation. So if we put together that volume's inversely proportional to pressure, so that's how we got PV is equal to a constant. We had V over T is equal to a constant at constant pressure and quantity. V over N is equal to a constant. So we have volume over moles is equal to a constant as well. So we have these equations that we could use individually to relate the 2 of those quantities together with those 3 laws, or we could put them all together. That volume is inversely proportional to pressure, but directly proportional to quantity and temperature. So just V is directly proportional to N, so it's up on the numerator, temperature as well, and then pressure is in the denominator. And so what this leads to is pressure times volume is proportional to N over T. And then what you use to get rid of the proportionality constant is you just throw in an R and then have that as an equality now. So that's where the ideal gas constant comes from, is that if you're saying, sort of like PV over NT is equal to a constant, you boiled it down to just a single constant, then that constant is what you call R, the ideal gas constant. And so that's kind of how we've situated or led to the discovery of, or just the ability to derive the relatively straightforward looking ideal gas equation, PV is equal to nRT. And so then if we come back to Avogadro's finding that you have a mole of gas, so 1.000 moles of a gas, of an ideal gas occupies this volume, I guess 22.414 liters is slightly more precise, liter at STP, we can then calculate R. So we can calculate what the gas constant is, given that at 1 atm, we know the volume of any gas is 22.414 liters, and then that's for 1 mole of the gas at that temperature. So if we do that math there, so if I take 22.414 and I divide it by 273.15, I get 0.8206. If I just round this to 4 sig figs, is generally what we're going to use this to. Maybe I'll go to 5 here, 82057, since all these do have 5 sig figs. And the units here would be liter, atmospheres, and then over mole Kelvin. And so this is how we derive the ideal gas equation. That's a 5. So 0.082057 liter atmospheres per mole Kelvin. And so more commonly, you see that unit right here. And rounded to 4 sig figs tend to be how many values we use this unit to. We're going to use this unit here a lot in problems. And then you see some other units as well that aren't super duper important. One of them becomes important later, and we'll show you how it's derived later. That one being this number, 8.314, for these 2 numbers here. So we'll see these derivations later. But then if we want to convert to other units, usually we just convert the pressure. Like you see, like the torr, like if you imagine that this would be 760 torr, and we can convert 1 atm to 760 and rederive a gas constant in torr, liter torr per mole Kelvin, we probably wouldn't need this number here. Instead of looking up this number here, we could just, if we have a pressure unit in torr, we want to use the ideal gas equation, just convert the torr to atm and use the 0.08206 liter atmospheres per mole Kelvin unit. So we're going to almost always convert pressure units to atm. Later, when it doesn't make sense to do that, we'll define and show you why it is important to use the other value here. So the 2 key units here that matter are this number and then these 2, which are the same number. But we'll see why the 8.314 is used when we get later in the course. Now, we can also relate the ideal gas constant to densities and molar masses. This is where we will pick up from on Monday, is looking at the relationship between the ideal gas equation and densities and molar masses. All right, guys, that's it for today. Have a great day.